Finally, we have reached the last module of this course, and in this module our plan is to discuss some of the results that we could not discuss in its full detail, and we won't be discussing it in full detail, but some of these results are foundational results, and therefore it is important to know the results because they will be referred in several occasions whenever you are talking about mechanism design. And also we will give brief outlines of some of this proof of the results, such that later on when you see the complete proof, or if you are interested you can take a look at the complete proof. They will be in this outlines will be useful. So the first result that we are going to discuss is the interplay between efficiency and budget balance. So we have already discussed each of these properties in detail, and we have also seen mechanisms which are efficient and which are also independently budget balanced. Now in this module we are going to discuss what is the interplay between them, and we'll see that there exists a tension between these two. There is a uniqueness about this Groves class of payments or the mechanisms that uses the Groves payments for efficiency. So it says that so we are familiar with this efficient allocation rule. It picks the allocation that maximizes the sum of the valuation of all these players. So in this context, the result by Green and Lafont, and also independently found by Holmstrom, says that if your type space is sufficiently rich, and we are not going to discuss much about how rich it is, so just for idea building you can imagine that it is as rich as the unrestricted domain. All that you have is these types are mapping the allocations into this set of real numbers, and there is no additional restriction put on it. In that kind of a rich domain, every efficient and DSIC mechanism is a Groves mechanism. So this is quite a strong result. It characterizes the space of efficient and DSIC mechanisms subject to the condition that the type space is sufficiently rich. That mechanism must necessarily belong to the Groves class. So what is the idea behind this proof? So we are going to just consider the proof outline for a very simple setting, a two alternative setting, and of course n players. But the idea of extending this result, this proof for more than two alternatives uses essentially the same idea that we are going to discuss. So what happens in this case? So suppose the type profile is T. So T stands for T1 to Tn, and the corresponding welfares of this players at this alternative A and B are given by this, some of the TIs at A and some of the TIs at B. Now we are going to assume this happens whenever the sum of the valuations at A is at least as much as sum of the valuations at B, then A is going to be chosen. So I mean the other condition that tie is broken in favor of B will be identical. Now what we are going to do in this context is we are going to assume that the valuations for all the agents except agent I are going to be held fixed to T minus I, and the valuation of player I, even for the alternative B, that is also going to be held fixed at Ti of B. So the only degree of freedom that we have in this context is the Ti of A. So if you want to draw a diagram, you can see that for all the other players, so this is the player direction and this is the alternative direction. So for all the players except agent I, their types for both these alternatives are going to be fixed, and for player I, B is also fixed. The only change that one can have is at Ti of A. Now given this degree of freedom, there must be a threshold point of Ti star comma A, such that whenever you extend, so if the Ti of A is more than that threshold value or at least equal to that threshold value, then A is going to be the outcome, and if it is not, then B becomes the outcome. because there are only two outcomes in this case. So you can draw a picture like this, and TIA becomes the thresholding point, and for all the points above this, you have A as the winner, and anything below that point, B is going to be the winner. Now let us consider two cases. So we know that this mechanism, the mechanism that we are considering, is DSIC. So therefore what must happen is, when suppose this TIA is slightly above this threshold point, so it is somewhere here, let's say, where this difference is epsilon, and we are going to assume that epsilon is positive. So what happens is, when player I, so because this is DSIC, when player I reports his type truthfully, then because this TI of A is larger than TI star of A, then this must pick A as the outcome. So therefore the valuation player I gets is this, which is the TI of A, and the payment that he is going to make is PI of A. Now this is a point which we might not have explicitly mentioned, but this is very easy to show, that that payment for a player has to be the same for an allocation. So if it happens that a player, by changing its type, cannot change the outcome, then the payment that he is making must be equal in both these two cases. So let's say player I has TI, where the other players have T minus I, and another type, which is Ti prime and T minus I, and the outcome in both these cases are actually A. All that I mean is they are not changing. So then the payment that player I should make in both these two profiles must be equal, because if it is not that, then it could be manipulable. So this is easy to show. If you write down the expressions, you can show it clearly. So all that we actually need is the payment at a particular alternative, and that is what we have written here. But if player I actually misreports something, so let's say he misreports something else. So if he misreports anything within this interval TI A, so greater than or equal to TIA, the outcome does not change. So the only way it can change its outcome is by reporting something which is smaller than TI star of A. In that case, if the outcome changes, then he gets a different valuation for that. So that is the value, the revised value and the revised payment. But because this mechanism is DSIC, this must not be larger than the valuation before. Similarly, you can write it for a different type, where the type itself now is smaller than Ti star of A. So this is something living somewhere here. Again, delta is positive. So this is something living something there. That means if he reports it truthfully, then the outcome will be B. So the player I should have the valuation for this outcome B, which is the outcome when he reports his valuation truthfully, and he makes a payment of this. That must be at least as much as if he reports something else. So suppose he reports something different to change the outcome, but in that outcome at A, what will happen is this, he will actually get the valuation of Ti prime of A. He will not get the valuation what he has reported. So he will get this valuation minus Pi of A. So this is the implication of DSIC. Now from these two things, if we consider the fact that both epsilon and delta were chosen arbitrarily, and you can make it arbitrarily small, you can actually take the limits and find this equality. So essentially you will see that you get this inequality in both directions. Therefore it must be an equality. So these two things, Ti star A minus Pi of A, Pia, and Tib minus Pib should be equal. This difference should be equal. Now we also know that Ti star of A is the threshold of this efficient outcome. So if something is changing, so we know that Anything above that, if it is above this ti star of A, the efficient outcome gives A. If it is below that, then the efficient outcome becomes B. So at that point, it must be the case the sum of the valuations must be same. And for all the players except agent I, nothing is changing, so their types are TJs. And for player I, this is going to happen. So ti star of A is the value, that is the type ti A at A, and the type of player I at B is given by ti of B. So both 1 and 2 should hold, as we have seen. Now we can see that there are similar terms. So ti star A appears on the left hand side in both cases, ti B appears on the right hand side in both cases. So you can just subtract 1 from 2 and get the following expression, which is the difference of this payment. So now we have collected together on the left hand side the difference of the payments at the allocation A and allocation B. And on the right hand side, we see that this is the sum of the valuations of all the players except agent I at the corresponding outcomes, efficient outcomes. So when the efficient outcome is B, then so you can see that you have a very much similarity with the Groves class. And indeed, with a little bit of work, we can show that this PIX has no other choice but to follow this structure, which has the second term. So the payment for the allocation that you are trying to find, the second term will be a negative term summing the types of all the other players except agent I at that outcome. And the first term has to be a function which is not dependent on T of I. Because if it was dependent on T of I, then we know that this equality cannot hold, because the payment at A, the type that gives the efficient outcome of A, is different from the type which gives the efficient outcome as B. So therefore, if it has to cancel on both sides, it better be the same. So HI, even if it was a function of TI T minus I, it has to be the same on both these sides. Let's say Ti prime and T minus I, where both these things. So this one, if it gives an outcome of A, and if this gives an outcome of B, they better be the same. So it should not happen that they are different, because if they are different, then this equality cannot hold. So what it means is that when the other players' types are held fixed, this function which you can add to the payment, that function cannot depend on the type of this player I. So that is the first part about the structure of the payment, which comes from the Groves class of payments. The second result, due to Green and Lafont, shows that no Groves mechanism is budget balanced. Formally speaking, it says that there does not exist PI of G, a payment of the Groves class, such that if you take the sum of the payments of all the players, and then it equals 0. Why is it not possible? So let us look at again a very simple proof sketch, considering again two alternatives, and the two alternatives are pretty simple. So suppose this is a public project, and if the project is undertaken, that is the outcome, the alternative that is picked is 1, then the players get some kind of a positive valuation. Otherwise, it is getting 0 value. Now we are going to assume for contradiction, suppose there exists some function hi, because that's the only thing that is the variable in the Groves class. there exists some HI such that the payment, the sum of these payments, if you want, you can say this is a gross payment, that becomes equal to 0. The sum of these payments equal to 0. Now we can consider two types of player 1, let's say W1 plus and W1 minus for player 1, and one type for player 2, such that these things happen. So if the sum is positive, the sum of the valuations for these two players is positive, then it means that the sum of the welfare is essentially going to be positive. So therefore it makes sense to build this project, since that is going to be the maximum. If the sum of the valuation is negative, then if you just pick this outcome of 0, that the project is not undertaken, that maximizes the social welfare. Right? So in that case, both these players get a 0 valuation, 0 payoff, and that is better than where the sum is going to be negative. Now we can apply the property of budget balance. We have assumed that this is going to be budget balance, so we know that the payment for player 1 will be H1 theta minus T minus 1, which is W2 in this case, minus the valuation, the sum of the valuation of all the players except agent I. And since there are only 2 players here, this is just going to be W2. So notice that in W1 plus W2, in this type profile, the outcome is 1. That is, the project is going to get built. Similarly, you can find the payment for player 2, which will be this, and that the sum should be equal to 0. Now look at the other type profile where the outcome is actually 0, so that the project is not built. So therefore this the sum will be just the sum of the H functions. Now we can simplify just by eliminating this term H1W2, and we can arrange it in a way that on the left hand side you have W2. Now on the right hand side you have the function, you have all the terms that are functions of W1. Right? Now you have to satisfy this equality, because this is a budget balance condition. This equality has to be satisfied for all such W1 plus W1 minus and for W, such that these two inequalities hold. Now this is impossible to get satisfied if you just carefully look at it. So this is a very kind of a sitting on the edge condition, and this has some flexibility. So for instance, because this is a strict inequality, you can perturb the value of W2. So maybe change W2 to W2 plus epsilon slightly, such that none of these inequalities get changed, and don't do anything to W1 plus and W1 minus. So therefore on the right hand side it remains the same, but the left hand side actually changed, and that cannot happen. So therefore this condition can never get satisfied. This is essentially the essence of the proof of this impossibility, that no gross class of mechanism can actually be budget balanced. So combining these two results, we can actually say that if the valuation space is sufficiently large, then no efficient mechanism can be both DSIC and budget balance, because efficiency and DSIC automatically will give you gross class of mechanisms, and we have seen that gross class of mechanisms cannot be budget balanced. So we get this corollary. So now you see that there is a tension between efficiency and budget balance whenever we are talking about DSIC mechanisms, and also considering sufficiently rich type space. So what can we do? So as before, we are going to relax some of these conditions. So one approach is to weaken the solution concept from DSIC to BIC for positive results. Now what can happen is, again, we can define a prior, which is a common knowledge, and we can define a payment which is again dependent, which is an expected payment. So player I observes his own type, and it has a belief which is coming from the common prior about the types of the other players. So therefore, instead of the mechanism designer, instead of charging the actual payment after the realization, they are charging the payment which is an expected value of those realized values. So therefore, the allocation rule still remains the same. It is still the efficient allocation rule, but the payment rule changes slightly. So payment rule becomes as shown here. It will be 1 by n minus 1 multiplied with the sum of the valuations, or sum of this delta values for all the players except agent I, and then subtract out this delta I of Ti as shown here. This payment rule has a name. This is after the inventors, Dopremo, Gerard Verret, and again independently done by Arrow. So the mechanism is called DAGVA, giving credits to all of them. Now we'll see that what are the properties that this payment rule does. So it implements the efficient allocation rule. The allocation rule is same, but it implements that in Bayesian-Nash equilibrium instead of in a dominant strategy equilibrium. So why is that? So it's easy to see that what you are going to do is you are going to take an expectation of T minus I given Ti, and then the rest of the thing is again very careful manipulation of these terms. We know that Pi DAGVA is nothing but this term, and you can see that the second term that we had here. So let's go back here. So the second term, which was delta I of Ti, which is nothing but the expectation of the types of all the other players at this efficient allocation A star of T, and this is summing over all the players except agent I. And now that is being subtracted. So if we club that together with the first term, the Ti term, then what we get is the sum over all the players. The second term, you can already see that because these are only, these delta j's are functions only of Tj, because the other terms has been taken the expectation over. So this term essentially does not depend on Ti. So all that depends on Ti is this first term. Now we know that by definition of A star, that is this efficient allocation, this sum is going to be getting maximized. I mean, this is getting maximized for every type profile, so it will also get maximized even if you take some expectations. So this inequality should always hold, even if player I reveals his type untruthfully. So for this change, the inequality should hold, and therefore you can again write this back in the same way that we have written before. So this mechanism, so this is the utility of player I when he is reporting his type to be Ti prime. So this shows that the DAGVA mechanism is Bayesian incentive compatible. Now to show the other property, that is budget balance, you'll have to take a sum over all these payments. And now you can see that here inside the first summation, you are summing all these delta j terms except one term. So if you sum it n times, you are going to get every delta j term n minus 1 times. So that is the first part, and the second part is of course sum of this I in n. So these are also, so again this will be 1, and these two things will essentially cancel out. You can actually ensure that the mechanism is budget balance as well as Bayesian incentive compatible. All right, so that is the result that we have. So you can weaken this equilibrium notion to get the budget balance even for the unrestricted domain. Now the question is, what about the individual rationality constants? So turns out that DAGVA is not interim individually rational, and in fact there is a kind of a negative result which is shown by Meyerson and Satterthwaite. It shows that in a bilateral trade, so what is a bilateral trade? Which involves two types of agents. So one agent would be a selling agent, and the other agent will be a buying agent. No mechanism can simultaneously be Bayesian incentive compatible, efficient, IIR, and budget balance. So all these good things cannot be satisfied together, and that is a kind of the impossibility result, Meyerson-Satterthwaite impossibility result. All right, so let us conclude our discussions at that point. to help you understand or remember the properties that we have seen in the modules, in different modules of the mechanism design, let me give you a summary picture what we have discussed so far. Maybe this picture will get engraved, and that will help you remember some of the results that we have proved. So on the left hand side, what we have drawn here is the type space or the valuation space, if you like. I mean, this could be different depending on which kind of domains we are looking at, which kind of applications we are looking at. But that is the domain of the social choice function. And on the right hand side, we have the space of DSIC mechanisms. So here we are considering only dominant strategy incentive compatible mechanisms. So the largest class is the unrestricted domain. So unrestricted preferences, and we have seen that if we allow all possible ordinal preferences over all the alternatives, then by Gibbard-Satterthwaite result, what you get is a dictatorial rule, Satterthwaite. Okay, so that is the first result. Then we have restricted from this unrestricted domain. We went to the single picked domain with the property of anonymity and ontoness, and using the results of Muller, we have seen that mechanism is a median voter rule. So there does exist some non-dictatorial rules which are median voter rules. Now we have also gone to the task sharing domain. So that is also a special subclass of the domain of the unrestricted domains. So there we have imposed these conditions of anonymity and Pareto efficiency, and due to the results of Sprumo, we have seen that this uniform rule uniquely characterizes this space. Now then after that, we have actually introduced the mechanism with transfers, and that domain, the quasi-linear domain. Roberts' result says that the mechanism that can be DSIC in that quasi-linear domain actually is a superclass. It includes dictatorial rule, it includes several other rules, and it is the class of affine maximizers. In particular, if you are looking at only the efficient allocations, the efficient rules, then by Green-Lafont, you know that is going to be the Groves class, which we discussed in this module itself. And if you impose efficiency and budget balance together, then you get nothing. So that is not possible. Then we have also briefly discussed about the space of BIC mechanisms. In fact, not in very detail, but in the quasi-linear domain, if you look at the efficiency and budget balance, then we know that DAGVA mechanism essentially satisfies this property. And again, due to Meyerson's and Satterthwaite, we know that if we try to impose the BIC, efficiency, budget balance and IIR together, then we get nothing. So that is an impossibility result. But we do have some sort of a positive result when we are talking about the quasi-linear domain, but for single item allocation. So that special subclass, if we look at the DSIC mechanisms, the result turns out to be that it is the class of DSIC mechanisms must have this property of non-decreasingness, and the payment of that rule should have the Meyerson's payment rule. Now if we relax this idea of DSIC to BIC, then we get a very analogous result, which is the non-decreasingness in expectation, and also a modified payment, which we can also call the Meyerson's payment in the context of BIC mechanisms. Now then we actually looked at the optimal mechanism, which maximizes the revenue earned by the auctioneer, and if we want to have the BIC mechanism along with that optimality constraint, then we have a very special thing like the reserve price auction. So this is the space of mechanism design that we have discussed. So hopefully these three pictures essentially succinctly summarizes all that we have discussed. Thank you very much for attending this course till this point.